It's a pleasure to have Mandy Cheung from Harvard, who will tell us about family Floer mirror and mirror symmetry for rank 2 cluster varieties.
Thank you very much. Thank you for Mahama for inviting me, and thank you all the organizers for inviting me. It's such a long while not seeing you all, and it's so nice to see all of you by Zoom. And I must mention that one of my collaborators of this project, Yu-shen Lin, will be here, so I will direct him to all the technical questions. As the title suggests, there are two parts of the talk. The first part is about family Floer mirror for cluster variety. The second part is about the more general case mirror symmetry for that. The first part will be somehow overlap with the talk I given before, but it's like a good recap of how we obtain the second result. And this is a joint work with Sam Bardwell-Evans, Hansol Hong, and Yu-shen Lin. Okay, cluster variety. Okay, as the title suggests, what we care today are cluster varieties. What are they? There are actually different ways we can define cluster variety. The one thing we can do, how we can see is going up. Usually, the standard that if you are coming from the algebra side, the definition we can see is going torus by some mutation map, something like that. We have two torus. We have this growing map x to x times 1 plus y, and then grow a bunch of it to have cluster variety. But then as a geometer, people usually don't like this definition and ask like, why do we in particular want to glue the tori like that? So here is an iteration, which is this gluing can be seen as blowup of toric varieties, which here we have C2, x equals to 0, y equals to 0, and then we have this divisor here, and then we blow up at the point 0, -1, which is like that, very standard thing that we do. And then that's what Hansol 1.2 tell us, which is where we blow up at this point, we are having our blow up lies in C2 cross P1 defined by this relation. And then what we do is we want to look at the open piece of this blow up. And then we sort of want to have a covering of this open piece. And then we have the first one is just covering our original torus. Well, C2, yes, well, torus here because we are open. And then second part, we want to cover the exceptional curve. And then the thing is, we look at the transition map. And this transmission map, one thing here, I know I'm a bit quick here, but here how I obtain this, like the second curve map is just simply by this relation here. And then if we combine all the algebra together, we'll see the transition map will be just exactly as this mutation map we've seen earlier. So you can see here, no matter we see cluster variety as going of torus, and blowing up of toric variety, they are basically the same thing. And then the second notation I want to introduce is this scattering diagram, which here I'm just telling you one coding only. And then scattering diagram basically encode the combinatoric of cluster variety, which to start with, we consider the lattice, rank n lattice, n and m. And then we have a scattering diagram is a collection of wall with some other conditions, which a wall, there are two components in the wall. The first one is what we usually think of a wall. It is a cone of codimension 1, and because it's called there's a cone in a hyperplane, so it lies on, it's a codimension 1, so it lies in a hyperplane. And then the second component of a wall is a wall function, which we associate the wall with a polynomial or power series of one variable, where this variable is actually a point lying in the hyperplane. Note that here, my point doesn't require to be in the support of the wall or not. It just needs to be on the hyperplane. Get the very standard example. This is called a cluster A2 example. And here my variable, I use a variable. So here is my notation, which is set to the M1, M2 is A1, M1, A2, M2. And this is a scattering diagram with 3 walls. And each wall comes with a wall function. And you can see here, say this A2 here, this is a polynomial, which is 1 plus A2. And A2 here is a point on the scattering diagram on the wall. And then once we have the wall and the scattering diagram, we want to pass the wall. And what do we mean passing the wall or path order product? Is we define an automorphism of the Lorentz polynomial ring, which, like in the picture indicate here, we have a scattering diagram and we have a wall that we want to pass over. We have a path that sorry, I keep on flipping the notation. That we want to have a path that going through the walls. And then, by the way, do let me know if I'm running a bit too fast on this part, because I will imagine most of you have gone through the notation already. But let me know, I will pause down. Like, I have this path that going over this wall. Okay, Mohammed, it's okay, right? And then,
well, it's okay for me, but I'm not sure I'm the right person to ask. So that's part of, there's a small issue here. But
okay, yeah, that's how I felt. I know it will be easy to other people, but anyway, this is a scattering diagram, and then we'll do wall crossing now. And then wall crossing is, now we have this path going over this wall, and this is our wall crossing. How does that look is, we have, we add on a monomial by keeping the monomial. And here I pass over this wall D, and this is my wall function. And then I multiply this wall function up to some power. And what does that mean? Let us again, like today's talk, everything will be illustrated by example. So let's illustrate what I mean by an example. Like, let me say here, I have this path order product add on this monomial set to the -1, 0. And then according to this rule, we keep the monomial and then we multiply this wall function, which is 1 plus set to the 0, 1. And then here I have the exponent term, which what I have is, here I have this monomial -1, 0. And then here what I mean by this n naught, I mean, or the plus minus, I mean the opposite, the normal of the wall that go against the wall crossing. So in this case it's -1, 0, and which is a 1. So you can see that's why I leave nothing here. And if I go back to my custom variable, this is simply 1 plus A1 divided by A2. And you can see here, this is the motivational idea. This one is actually nothing, but we can switch back to the x and y variable. So it will be y inverse map to. And you can see this is nothing, but just the custom mutation or grouping map we mentioned in the first slide. Maybe because we are pausing here, one thing to note or make you guys all upset about me is picking this opposite normal is a notation in the cluster theory, the cluster scattering diagram. But later on, I will mention this GPS scattering diagram. And what they do in their notation is they will choose the normal that go with the direction of the path. So be slightly careful when we were going over all the different notation. So here, one more notation about scattering diagram is consistent scattering diagram, which actually, in the example I just gave you, I gave you this example, but actually just two walls here is a scattering diagram as well, but this one is not consistent. What consistent mean is we consider a loop like any loop that go along in the scattering diagram, and we require that when we look over the scattering diagram, the corresponding path order product will be identity. In this case, when you do the computation, it is not. So it will be used in the lateral half of the top, so that we need to add one more wall here to turn the scattering diagram to be consistent. But then let's go back to the cluster theory. This is our scattering diagram, the cluster scattering diagram. And then to define a cluster variety from a cluster scattering diagram is we associate each maximal cone of the scattering diagram with the corresponding the torus of the corresponding dimension. Here we're going to call the maximal cone as chamber. In this example, we are gluing five torus together, and then the gluing will be coming from this half order wall crossing map. And then in this case, we'll get the A cluster variety of type A2. And you can see here, I'm very careful stating that it's a A cluster variety than just saying it is a cluster variety, because later on we are going to see there's another type of cluster variety called the X cluster variety. And I must say here, a scattering diagram are defined with some type of injectivity assumption. In this case, in the first part of the top, actually all part of the top will focus on the dimension 2 case, which the assumption is satisfied. So we can independently with the big dragon and the combinatoric, and just to define the A and X cluster variety. Okay, this remark is for the cluster people. And if there's any cluster people, you can see this 5 torus is actually the very standard 5 set of the cluster in the cluster algebra story. So theta function, to motivate why we think about theta function, it is like, again, everything in this talk are just example. We be like torus, like C star square. We look at the function on the 2-dimensional torus are just Laurent polynomial, which can be written as linear combination of Laurent monomial. And here each Laurent monomial can be indexed by a set to length, set to lattice, right? So this is how we can immersion theta function, which is we associate each lattice point with a function on the cluster variety, which again the combinatoric is very long, which to define theta function is very long. Roughly speaking, theta function is defined by a collection of Boolean line with initial slope m and endpoint q. In the cluster theory, we fix the endpoint in what we call the positive chamber. Again, example, our favorite scattering diagram. This is our endpoint. Positive chamber means we have all the entry in the, everything is positive in the tuple. And then here we choose our initial slope is -1, 0. And then here we have our initial slope. We'll have a line with this initial slope, but the direction of the line as the remark here goes in opposite direction. So given the initial slope -1, 0, we are actually going 1, 0 direction. So the very first Boolean line is a Boolean line that doesn't bend. So it is this example here that I have a straight line with this slope going to this endpoint Q. But as the name suggests, Boolean line is something that it break, that it bend when it hit on the wall. So this is the second broken line here, that it bend over a wall. And how it bend? The bending is according to something we got before, the path order product, which we have set -1, 0. From our previous calculation, we have -1, 0, -1, 0 times this wall function. And actually you can see here the whole formalism. The one here means it doesn't bend because we skip the same slope. But then here we have the second term, which is -1, 1 here, which you can see the monomial change. And then here that just indicate we bend with that slope -1, 1. So this is the second broken line. And how a theta function is defined.
Mandy,
Yeah.
can I ask? So in this example, there's like coefficients, and the coefficients are both 1. Is this always going to be the case?
No,
Okay.
you keep the coefficient if it is not 1.
So somehow it's a broken lines with weights or something like that.
Yes, yes, you are very right. Like we are going to talk about tropical curve. It is with weight. Yes,
Okay.
the coefficient will be count. But yeah, like here, if I go higher bending, like you can see if I -2, 0, then I will have -2, 0 times 1 plus set 0, 1 square. And then we can see I'll have 3 terms. Like here, the monomial will go with the coefficient, will be set -2, 1, and then set -2, 2. And then the bending here, let me erase everything, will be 1 this, and then 1 that. And then for this one, I will associate with, go with the 2 as well. Yeah, because we're going to see like, yeah, there's like some type of bending and we include a coefficient as well. Thank you for your question. Okay, great. Seems people are following. So what is a theta function? Theta function is we look at the collection of all broken lines with this initial slope and the endpoint. And then what we do is we look at the part that associate to the endpoint, the monomial or the final piece of linearity that associate to this endpoint, and then we sum that all up. So this is a theta function associated to the lattice -1, 0. So let's still go back to our only example, c star square. Here it's not only that the function on the 2-dimensional torus are Laurent polynomial, but when we multiply 2 Laurent polynomial, it is still a Laurent polynomial. That is, it can, when we multiply 2 Laurent polynomial, it can still express in terms of linear combination of Laurent monomial. Which this is what I want to say is this is not only a vector space, even though I wrote it as a sum, but it is also an algebra. And that also work in the cluster world, which Gross-Hacking-Keel show that when we multiply 2 theta function, we can express in terms of linear combination of other theta function with this coefficient, where this structural constant can be expressed in terms of broken lines. And actually this one, I have this other work with Tim McGee and Lagrangian surface, which we work on this coefficient to give the tropicalization of cluster variety. But the story here is we have this multiplication relation here, so then the collection of theta function carry an algebra structure. And in particular, the algebra we want to care is what we call the middle cluster algebra, which the algebra generated by theta monomial, which we want the theta function to be not series but polynomial for the cluster variety A and X. And then for encounter have this conjecture that they conjecture this middle cluster algebra is the swing of regular function of our cluster variety, which this conjecture hold with some convexity condition, which is actually related to the positive polytope of my other paper. But anyway, let's go back to the mirror symmetry side. We have this is the part we did before is entire algebra, cluster theory. Why do we care today? So here we go. We have this Gross-Hacking-Keel mirror for log-Calabi-Yau surface, which we start with the log-Calabi-Yau surface and an anti-canonical bundle with all the good property, and then we look at the topicalization of this pair, which is an integral affine manifold with singularity and a Hong decomposition of this affine manifold. And what do I mean by this topicalization? Again, example, dp5 and string of 5 minus 1 curve. And then what we did here is we look at like each intersection, like we have 3 of them, like the intersection of the divisor, and then we can also, by using the toric node relation, we can draw the cone that associate to the intersection of divisor. In this case, we have 5 ways, and then at the end, but like here we have this relation. Actually, we have this D1 to D5 that associate to V1 to V5. And the relation here is V1 plus V3 is V2. So that's why we can draw this this cone decomposition by algorithm. But then here it comes when we go to the quote-unquote sixth way, it should be going back to the first way, but actually it is not. So here is the affine structure that comes in. We want to have an affine structure that cut out this piece, this region, and glue the 2 ways together. So that's why this is affine manifold, but not SAP2 or R2. And then here, the divisor will give us the cone decomposition. And then here, once we have this, we want to draw a scattering diagram again. Again, we have wall. In dimension 2, the wall are just way. And then again, we have function that are associating to the wall. But one thing to note here is in cluster scattering diagram, the wall are basically cluster mutation formula. But here what we have the wall is, we have the wall are coming from some Gromov-Witten invariant, which we'll talk slightly more later, but now just take it as we have some curve counting invariant that give us the wall. And then here, in this case is we have this cone decomposition. Those are the wall. In DP5, we are not adding more walls, but in other cases, actually, we might add more wall. But what Gross-Hacking-Keel show that is this scattering diagram, this is called the canonical scattering diagram, are consistent as well. And then from there, we can repeat the same game as the cluster theory. We associate each chamber with the algebraic torus and glue the torus by wall crossing. And then those are the similar. And then we can again define theta function associated to each lattice point. And then here, this is what Gross-Hacking-Keel's work as well, which this collection of theta function will form an algebra. And then as an algebraic geometer, which they are, we have an algebra, we take the spread of it, and that is the proposed mirror. So you can see this is the story, how it is tightly linked with the cluster theory as well. So as the title suggests, we will talk roughly about family 4 theory, which I guess the audience might know better than me. This is with Fukaya Ota Ono's work, which we start with a symphatic manifold, and then we consider the Lagrangian submanifold of it, and then the FOOO tells us that we can define the A infinity structure on the cohomology ring. And then once we have this A infinity structure, we can define the Maria-Cantan space, which is kind of the zeros of this A infinity structure. And then to formulate in our upcoming setup, we are dimension 2. And here, if we are considering the L is a special Lagrangian, and then here is, we are dimension 2, so real dimension is 4. So in this case, we'll have our Maria-Cantan space are actually just H1, which you can see a torus here already. And then the story of what Foucault proposed for the family form mirror. Here is we have the pseudo isotropy of the A infinity structure of the cohomology ring, which again you can see is similar to the GHK theory. This map actually we call the canting of the holomorphic disk. And then the story goes by very similarly, at least from my point of view, as the GHK, which is then we grew the Maria-Cantan space according to those maps. And then Foucault suggests that will give us the family form mirror. And then with Yu-shen Lin, which is here, what we establish is for rational elliptic surface, we establish this dictionary between the family form construction and this Gross-Hacking-Keel or Gross-Hacking-Keel mirror construction, which you can see here on the GHK construction, we emphasize we have walls on the scattering diagram, which are weight, and then on the A side, which will be the loci of the SYC fiber binding the holomorphic disk. And then we have the function here, which on the A side will be counting Maslov index 0 holomorphic disk. And then the wall crossing from the GHKS point of view will be isomorphism of the Maria-Cantan space induced by the pseudo isomorphism. So what we do is, like, once, at least from my point of view, this is so similar, like we cannot stop ourselves and put the idea from this GHK or cluster theory to the family mirror side. So this is what we have, which is on the Gross-Hacking-Keel Siebert cluster theory, we have the Laurent polynomial. This is how the cluster theory starts. We have the Laurent polynomial. The spread of the Laurent polynomial gives us the torus, and then we grew the torus by wall crossing. And then on the analytic side, we have the Tate algebra, and then we take the spread of the Tate algebra, which here in general will be a rational domain, but in our case will be an analytic torus. Let me emphasize here, like, kind of usually say it as kind of an analogy from the cluster story, but actually going from this, one of the big part in the joint work with Yu-shen Lin will be how to obtain this analytic torus. Because you can see here in the cluster theory or Gross-Hacking-Keel or Gross-Hacking-Keel Siebert mirror, we are associating the chamber with the algebraic torus. But if you think about it torically, it's not that, right? So in this case, what we want to do is we will want to take the inverse of the tropicalization. But so what we want is we want like the lattice is almost like the whole, the lattice that corresponding to each piece of gluing is really a whole lattice, because like here, if we just have this, that will be C in the toric. So that is actually one of the main part in our construction. But anyway, once we establish this, we again grew the analytic torus by the wall crossing and by Gaga, that we can lift it up from the algebraic world to the analytic world. So this is what we obtain. I know it's super long, and if I want to say it. It's a journal with Yu-shen Lin, which is here, that we look at 3 types of equational elliptic surface, which is of singularity 2, 3, 4. And then the family 4 mirror of this 3 type are actually DP5, DP6, which are cluster variety of type A2. That is the scattering diagram we keep on talking, and of B2 and MG2. So you can see how we explicitly construct the example for family 4 mirror. But here you might be like, okay, can you do more? Here is only 3 examples, right? So that is like the second part of the talk of today, which how we can go from this 3 example to a slightly more setup. So one thing when we were talking about the Gross-Hacking-Keel mirror is that the wall function are associated to curve counting. And what curve we are thinking? There will be a bunch, but the one thing, the first thing I want to mention is this tropical curve or curve. Okay, the curve here, like we keep on talking about scattering diagram. It seems to be very combinatoric, but actually, one can emerge scattering diagram is the tropical picture of the Lagrangian fibration. And the reason that why scattering diagram dictate so many geometry is the wall are actually, one can imagine the wall are the tropicalization of holomorphic disks, which can see as a tropical curve or tropical disk. I'm sorry, I don't know why my computer keep on looping. So what are tropical curves? Tropical curves are weighted graph immersed in Rn with rational slope, and each vertex satisfies what we call the balancing condition. And the balancing condition is simply like this. At each vertex, we look at all the edges that going out from the vertex, and then the summing of all those outgoing direction will be 0. And like Muhammad suggests, there might be weighting as well, but here is, let us simplify the whole story, which is at each vertex, we look at all the edges adjacent to the vertex and then all the outgoing direction with multiplicity, summing up will be 0. And then this is another example of tropical curve. You can see here at each vertex, like when we sum up all the outgoing direction, it will be 0. And then how can that relate to scattering diagram, which is this picture? This is the underlying is our favorite scattering diagram, and we can see here that, well, it's wet already. There is a tropical curve lying underneath the scattering diagram. That's why in the first part I'm saying like having consistency will be important for this second part of the talk, because the construction of consistency scattering diagram actually inherit discounting or constructing tropical curve from the original scattering diagram. So the work of Gross-Hacking-Keel show that the wall function here, again skipping all the technical detail, like the log of the wall function here, actually the coefficient correspond to tropical curve counting. Here our talk are just only focus on the rank 2 or dimension 2 example, but let me mention that Mendel have generalized this this result to the general dimension setup. So now we have a tropical curve, but then why do we care? We have McConkin and Lucino Sieber tells us that this tropical curve counting is the same as holomorphic curve counting. And what we have with Sam Bardwell-Evans, Hansol Hong, and Yu-shen Lin is we show that the tropical curve counting are the Maslov index zero discounting for simple blowup of toric variety. And then here comes a very, very rough story of how things go. It's super rough, which is we consider a collection of primitive vector in rank 2. And then we will define an initial scattering diagram of this form, which is we have all those vectors, and then we look at the line that with that direction. And then the wall function will be 1 plus mi. Again, notice that here now we go back to the GPS scattering diagram. So the choice of normal, we flip the direction of the choice of normal. So that's why I don't have a minus here. So, but you can see here, this scattering diagram is not consistent. It is initial one. So what we'll be considering consistent scattering diagram coming from this initial one. So we shall be adding more ways from the initial one. And actually each adding here, okay, it's not correct, but then they are all, each way that we add actually corresponding to some tropical curve with the given incoming direction. So the geometry behind is all what space that we are counting the curve, right? So it is, we look at the toric surface defined from this fan, which is here, we have a collection of all those vectors, and then now we look at the fan that defined from all those primitive vectors, and then this is a toric variety. And then we look at the toric divisor associated to each fan, and then we blow up the toric variety at those divisors, which we are going to see in the toric case, like this is in the Castor case, this is kind of the story we have. And then the walls of this GPF scattering diagram will give the counting of the genius zero curve intersecting this blow-up of the divisor with some tangency condition. So here is the setup, like we have a bunch of primitive vector. On one side, we can define the scattering diagram. And then on the other side, we can see as a fan. And then we have the toric variety, and then we blow it up. And then the wall function, the curve counting, the wall function will be counting the curve on this blow up of the toric variety. So, and all here are the GPS story. And with Sam Bardwell-Evans, Hansol Hong, and Yu-shen Lin, we kind of repeat the story from a synthetic point of view. We define the Lagrangian for scattering diagram, which now the wall function are corresponding to counting of Lagrangian fiber that bound the Maslov index zero disk. And then what we show is this Lagrangian for scattering diagram that we define is the same as the the GPS scattering diagram. So then we wrap up everything and then show that the counting are the same by this tropical holomorphic correspondence. But here, let us go back to this talk will mostly focus on the Castor story. So let us go back to how we apply this finding to the Castor variety setting. So now we have no choice but get to more technical part of the Castor variety. So Castor variety can be defined by collection of data called fixed data and seed data. Fixed data are lattice and skew symmetric forms, and some integer di. And let me emphasize here that in the Forman-Sawinski well, or in the general cluster algebra story, they define it by something called skew symmetric matrix. That is a matrix multiply a diagonal matrix will be skew symmetric. And in the GHK world, they first have the skew symmetric form, and this d integer di is actually it's kind of like this diagonal here, but then turn this skew symmetric form to be a skew symmetric matrix. So this is the initial data, and we have something called the seed data, which is the basis of the lattice n. And then from here, we can look at the dual basis and the dual lattice, and then we look at the scaling. Because like here, as I said, like actually what we care is the skew symmetrizable matrix. So we look at the scale lattice with the basis scaled by the 1 over di. And then we have two lattice, two kind of dual lattice, and hence we have two kind of dual tori, which take the span of the corresponding Laurent polynomial. And then we define the A and X cluster variety with the two different type of the A and X cluster mutation. Note here is notationally heavy here. Just a few things to remember. The X mutation are the pooling of 1 plus set to the EK, which is on the lattice n. And then the A mutation is the pooling of set to the VK, which VK is kind of the skew symmetric dual of the EK. And then up to some power here. Then one more thing here, one more notation is here we emphasize we start with a skew symmetrizable matrix. So that's this called Lennon's dual, which we can imagine the Lennon's dual of the fixed data are just taking the transpose of the original fixed data. It's just taking the transpose of the skew symmetrizable matrix. Like here, I really want to go slow, or like we talk a bit more about technical detail here, because from my understanding, most people are only working with skew symmetric case, but not skew symmetrizable case. So here, like we'll go slow with how this di, when the di not equals to 1, how the story go. So, but anyway, here we look at the transpose of the original skew symmetrizable matrix, and then the same story goes. We can still define a lattice, and then we can still define a all the bases and then everything. So here is how we can interpret that in terms of the fixed data and seed data language. So then now we have the fixed data, the lattice will be NL and dual, which is coming from the scaling of the original lattice n here. I have the n here. And then I have the scaling here is actually coming from the DI. And then I have the integer is coming from this D, which is the LCM of the D divided by the DI. And then now we take the skew symmetric form as the original skew symmetric form divided by this LCM. And then once we obtain this, the whole story just follow as what we have before. So let us go over an example to see how these things go. We have a two-dimensional lattice. The skew symmetric form are just this 0, 1, minus 1, 0. And now we have D1 is K, D2 is L, where K and L is pole time. And then if we go over all the computation and combinatorics, the mutation function of the A mutation will be 1 plus A1 minus k and 1 plus a2 to the L. But then on the other hand, when we look at the Lagrangian x mutation, there will be Lagrangian x1 the whole thing to L, and then the second map will be the whole thing to K. Like here is a very weak intuition we can see thing. From A to X, you can see if I'm not taking Lagrangian here, it is kind of like pulling out the exponent. And then the Lagrangian here, like I said, is transform. It's kind of flipping the exponent. So you can see here, I have this flipping here, and then the x A to X is pulling out the exponent. This is a very weak idea. You can see if we have three integer, it's hard to say how we flip, but this is what I hope one can have in mind, how we play around with this Lagrangian A and X mutation thing. But this is the conjecture proposed by the emergent for curve, maybe consider Solomon as well, and JHKK, which the A cluster variety are mirror to the Lagrangian of X cluster variety, and the X cluster variety are Lagrangian to the Lagrangian A variety. So this is what we want to know then, using what we have with Sam Bardwell-Evans, Hansol Hong, and Yu-shen Lin.
Sorry, can you just repeat what you said? You're saying that, I see, okay, fine. A is so, but what does this tell me something about the A cluster variety and the X cluster variety for the same, how are those related?
Those are proposed mirror. Like it is proposed that the mirror of A's will be Lagrangian of A X variety. The mirror of X will be the Lagrangian A variety. And this is what we aim for.
So this equivalence, no.
Yeah, I'm sorry. That means mirror. It's like poor typing.
Okay. And there is nothing explicit that you can say about the A and the X of the same cluster data.
If di equals to 1, then Lagrangian will be just itself. Then they will be, then you can see I can just drop off.
Okay.
I can just drop it off. But I do believe in general, A and X are not supposed to be mirror.
Okay, thank you.
And always is so. Yeah, I know it's a bit but people have asked me about the iteration. Like here you can see if you are in maybe some of my other collaborators talk like Tim McGee or Fellow Ledger, they will talk more about it. Which here you can see I was rough, but scattering diagram lies in the lattice, which is M sub R, not M sub, which actually they correspond to the tropical point of the Lagrangian X. So actually from the point of scattering diagram, this Lagrangian is inherent there already, because I here my D is not in. Well, though M sub R and MR is the same, but when we define theta function, the lattice point, actually we already go to the Lagrangian side already. So that is why it is supposed that when A and X are mirror, there's like this Lagrangian involved. And most people will drop it out because most people I know they only work with skew symmetric case. But that is why I really want to go slow and mention this part here, because this is what we obtain with Sam Bardwell-Evans, Hansol Hong, and Yu-shen Lin. So So this is the cluster variety, and then we want to say how we have the cluster variety can seen as blow of toric variety. So now we go back. It's like exactly, you can say, actually, even though I have a lot of notation, I hope to convince you that I just keep on repeating the same thing in my talk. Like in the GPS story, we mentioned about, we have a bunch of primitive vector, and then we have a fan, and then we have the toric variety, right? So here is the story. Like for the A and X case, we consider the two fan coming from the DI and VIs. And then from there, we again consider the corresponding toric variety from the fan. And then we again look at the ways. I'm going to nail down to, well, this is a way anyway, like we look at the, in general dimension, like the way that correspond to the toric divisor. And then we blow up at the point on this divisor, which here the loci that we blow up seems, this one seems very technical, but again, let me convince you that this is nothing, because like here in the beginning, we said that x to x plus y. And then here, you can see here what we blow up is, we blow up at this point 0, -1, which this point is nothing but the 0 of x 1 plus y. So you can see here what I blow up is like nothing, but those are just the mutation that we have before when we talk about the A and X mutation. So we just look at the zeros of those mutation maps, and then we intersect with our toric divisor, and then we blow up there. And then this one, I'm just typing it up, and then we have this toric variety, and then we blow it up along with this ZA or ZX. And then cluster theory, we only care the open piece, so we look at the open piece of this blow up. And then this, according to GHK, Gross-Hacking-Keel, birational geometry of cluster variety, this U is isomorphic to the cluster variety of A and X, which is, if we think of it here, what I mean cluster variety gluing of tori. But now we can see how we can see the gluing of tori is basically the same as blow up of toric varieties. What we want to know then is cluster variety of rank 2. One thing to emphasize is rank 2 doesn't mean dimension 2. So I might start with my fixed data with the lattice and with general n dimension. What I mean rank 2 here is the skew symmetric form is rank 2. One example we have in our paper is like this, like A, for example, because think about it, all the odd-dimensional skew symmetric matrix are not of full rank anyway. So here, this is what we mean. Rank 2 means the skew symmetric form is of rank 2. So we have the kernel, which is lying inside the original lattice, and then this kernel will everything will give us a torus action on the Tn set. So, and then this torus action will commute with the mutation. This one means it commute with the mutation gluing, so that induce a torus action on our A cluster variety. So what we mean by cluster variety of rank 2 here is actually we want to look at this cluster variety but quotient by the kernel or the torus action. And you can see here is the dimension 2 things that we are looking at. So the story we one thing I want to note is like we originally want to use GIT and see if we can really just do quotient, it turns out we cannot do it, like there's some obstacle. But what we can do is we can just repeat again what GHK do. Can repeat again, which is here we start with lattice n, and then we have the kernel. And then what we can do is we just quotient, we look at the quotient and obtain a Venn2 lattice. And then we repeat the same story. We have the scaling, and then we take the dual lattice and so on and on. Everything we just repeat. And then what we do next is in the original caster story, we look at the fan coming from our EI. And now we look at how we quotient down those basis vector to this two-dimensional lattice, two-dimensional space. And then we still obtain a fan. And then we show that everything still follow. We have this blowup of this toric variety coming from this fan will be isomorphic to this quotient of A variety up to codimension 2. So here now we have a space. And then what we want to do is we want to repeat the GPS story. GPS story is we have a bunch of primitive vector. On one side, we have scattering diagram, GPS. And then on the other side, we have this blow-up thing, open piece of open thing. And then the GPS scattering diagram can the curve on this space. So now you can see here, we have the space. So we want to write down the scattering diagram. Maybe I have more. Okay, this is the scattering diagram. So this is the fan. And then the GPS story is we look at this collection of primitive vector, independent or not. And then we look at the line that with that direction, and then associate with the wall function. And I here, because we are quotienting, that we have EI here. We are here, let me emphasize one thing. That is actually one of the main part of our of our discovery. Like here we have our blow-up loci are coming from the zero of the mutation map. But then here, like in dimension 2, you can see those are just like polynomial, binomial in one variable. And then those zero locus of them are just pawns. And then fundamental theorem of algebra tells us that how many pawns that we have, which is just this index of VI, many pawns. So that's why here we have that many number of blow-up. So that's why on the scattering diagram, we overlap the walls with index of VI bar many times. So this is the scattering diagram, initial scattering diagram we have. But when we look at this scattering diagram, forgetting all the geometry, we can see that this scattering diagram is with some initial line as EI. And then here I have my wall function as something EI, right? Like remember when I said that A mutation is something 1 plus set VI, X mutation is something 1 plus set EI. So you can see here, this wall function here really looks like something like the X mutation or the Lagrangian of X, because I have the DI here that hints me the Lagrangian. That is really like the Lagrangian X scattering diagram. But more precise, again, because we are in rank 2 case, what we have actually is on the A side, we have the kernel K lies inside N. On the other side, we have the Lagrangian K also lies in Lagrangian of N that induce a morphism from X to K. And then that induce that we can see the X cluster variety as a family over the torus. So this is what we have at the end, which is this scattering diagram actually correspond to, in terms of algebra, correspond to the identity, the space of the, here we look at the identity, then we can look at the Lagrangian X of E, and then this scattering diagram will give this scattering X Lagrangian X scattering diagram at the identity, or the fiber of the identity. So you can say this is what we established with all the technical detail we went through with Sam Bardwell-Evans, Hansol Hong, and Yu-shen Lin. You can see roughly what we have is we have a quotient of A cluster variety, and then they are mirror to the Lagrangian of the X cluster variety, because we construct the scattering diagram. Here I put roughly because as we said when we are talking about the cluster algebra story, that is this Floer and Gonchar conjecture, which the middle cluster algebra is the same as the ring of regular function of the cluster variety, which is not known to be true or not in general. So what we have, we do have the scattering diagram for all the general cases. But if we want to talk about the algebra, we require the Floer and Gonchar conjecture whole. And then what's more is like we say, we show that this Lagrangian for scattering diagram is the same as the GPS scattering diagram. So we cooperate it. One thing here this first theorem is entirely algebraic geometry, but when we put the symplectic geometry in, which in our counting we require one condition, which is the blowup is not orbital blowup, just simple blowup. But once the blowup is just simple blowup of toric variety, then this mirror is not just a mirror from the GPS point of view, it's also a mirror from the Lagrangian for mirror point of view. So that is the story for Maslov index 0 disk. So one might ask, how about Maslov index 2 disk? Basically, Maslov index 2 disk book 9. I know over time I'll be quick, in 2 minutes I will finish. Assuming that divisor have no negative Chern number, and we have L is a miscible SYC fiber, and then we have the Maslov index 0 to discounting is the same as the weighted count of book 9 in the GHK story. So this is the A2 example that we really like. So those are the book 9 you can see. And then we have the cubic surface, which same have drawn this pretty diagram of all the book 9s, which we have the 21 this year, which agree with all the previous discovery with all those people. And thank you very much. Sorry for overtime. That's all today.
Thank you. Let's thank Mandy. And does anybody have any questions? So I wanted to ask, do I interpret correctly? Can you go back to like page 24 or something like that, where you have this statement where it said roughly something, something?
Well, it's like roughly depending on what you want. like I say, we start with a quotient of A variety.
Yeah, so that's what I want to ask about. So you're saying that somehow this Goncharoff prediction needs to be corrected by taking this quotient, and am I understanding correctly?
No, like here we do get the scattering diagram. I forgot how I did it. EL always. That is something we get. But the question is, from this scattering diagram, we want to get an algebra to construct the mirror. That is what judge K tell us that they want to do.
Mhm.
And to obtain this algebra, that is the unknown part, because we want the algebra to agree with, because like here we have a scattering diagram, we have an algebra. On the other side, we have a cluster variety. We want to look at the ring of function. Like if that equal or not is not entirely clear, and that is the Floer and Gontard conjecture that they conjecture that they are the same. So it is this step that getting the algebra to obtain the mirror, it is the roughly part that is under the Floer-Gontard conjecture or assumption that we have the algebra coming from scattering diagram is the ring of regular function of the cluster variety. But if we forget the algebra, we get the scattering diagram in full generality of rank 2.
Okay, so okay, but is this the statement that would have been predicted by Polkoncharoff? I mean,
which statement?
Well, that you know, you stated some kind of A side, the A cluster variety is mirror to the Langland dual.
I don't really know what they have written down, but it's only that I just know that the precise statement that Floer and Gontard, but the story is, yeah, like they are mirror to each other, and
now you're saying something more precise because you're saying the appearance of this quotient.
yeah. The thing is here they don't yeah, like, okay, I'm a bit hesitant to use the term precise or not, because they are looking at cluster variety, and what we do is we nail down to rank 2 case. But what we have rank 2 is not as usual the cluster variety, but we look at the quotient of it.
So let me ask a different way. So this statement is in rank 2 only.
Yes, because we are we just can't surface. So that is like, but rank 2, what I want to emphasize is not dimension 2, but we quotient out all the high dimensional thing to surface.
Yes, but, okay, I think I understand somehow that the blue wings are 2-dimensional in some sense.
Mm-hmm.
Sorry, now I'm getting confused. Can I interrupt and ask if I understand correctly? So basically we have a cluster algebra of rank 2, but things would be higher dimensional by default. And you're interested in a 2-dimensional quotient that keeps all the cluster mutation structure, but forgets the degenerate directions, right? Okay, and so that's the quotient that you have in the story here.
Yeah. Like we have one example of the A3, like in our paper, which is like you can see how we can do something, and actually only we write that I need to find out that that is also this paper by Yan Zhao. She's also computing our example much more carefully as well. But if you want something quick, we have demonstrate how rank 2 doesn't mean just dimension 2.
Okay.
We have like high dimensional and quotient it out.
So I have another small question. The diagram at the very end on the cubic. So the scattering diagram itself would be infinite, right? You only just draw a finite part of it because that's all that matters for the disk, the Maslov 2 disks, right?
Yeah.
Okay, thanks. Okay, thank you.
Any other questions? Okay, well, if there's no more questions, let's thank Mandy again.